Hi, you're right. This is our third lesson for probability. In this lesson, we're going to look at the laws of probability. So last lesson, we learned about compound events and the language of probability, in particular, and, or, not, at least, and at most. And then we learned about mutually exclusive events. Now, there are two laws in probability. The first one is the law of multiplication. So if we have two independent events, A and B, and we want to find the probability that they both occur, then all we do is multiply their individual probabilities together. And in probability, if we say the word and, it means times. So the probability of A and B is equal to the probability of A multiplied by the probability of B. Now, what do I mean by independent events? Well, independent events don't affect one another. So for example, throwing a coin and a die are independent events. It doesn't matter whether we get a head or a tail on the coin, it's not going to affect the outcome of the die. An example of dependent events is drawing two cards from a deck without replacing the first one. So depending on what we draw the first time, the outcome of the second one is going to be affected. Now we're going to go further into independent events in years 9 and 10. So here's our first example using the law of multiplication. Jana tosses a coin and a six-sided die. What is the probability that she throws a head and a six? Now we did this exact question in the last video just by listing the sample space. And then we found where heads and 6 appears, which is here, and so the probability is 1 out of 12. But let's have a look at how we use the law of multiplication. So we want heads and a 6. It's going to be equal to the probability of heads multiplied by the probability of a 6. Probability that we throw a head is 1/2. Probability that we throw a 6 is 1/6. Multiply those together and get 1/12. Now, it doesn't matter which method you use. You can use the law of multiplication or you can list the sample space. Here's another example. What's the probability that she throws a tail and a number greater than 2? Okay, so this is how we write it. Probability of a tail and a number greater than 2. It's going to be equal to the probability of tails multiplied by the probability greater than 2. Okay, probability that we throw a tail is 1/2. And then a number greater than 2, we want a 3, 4, 5, or 6. So that's 4 out of 6. And then multiplying those together and simplifying, we get 1/3. Okay, here's another example. A 12-sided die is thrown twice. Find the probability that we throw a 2 and then we throw an 8. So order is important in this case. So this is still an AND question. We want a 2 and then an 8. So we can multiply those probabilities together like this. So probability that we throw a 2 is 1/12. Probability we throw an 8 is 1/12. Multiply them together, 1 on 144. What about the probability that we throw a 2 and an 8, but in either order? Okay, what do you think about that? So we could do a 2 and then an 8, or we could have done an 8 and then a 2. Can you see that it's just going to be the same probability but just doubled? So we're going to take our 1 on 144 and multiply it by 2, which gives us 2 on 144 or 1 on 72. Now I mentioned before that you can use either method. You can use the law of multiplication or you can list the sample space. But sometimes we won't be given any context and so we can't list the sample space. Like this question. Events A and B are independent. Probability of A is 0.6. Probability of B is 0.2. Find the probability of A and B. And so all we're going to do here is use the law of multiplication because it tells us that they are independent events. So the probability of A and B, we multiply probability of A by the probability of B, which gives us 0.12. Okay, let's move on to the second law, which is the law of addition. So for two events A and B, the probability of A or B occurring is equal to the probability of A plus the probability of B. And in probability, or means plus. So if we say or, we mean plus. Now, did you see these words here? That's if the two events are mutually exclusive. So if they're non-mutually exclusive, we have to subtract this part. This is the double up. Do you remember me talking about that? So when A and B have common elements, we've counted the common bits twice. So we have to subtract it. Now, it's actually the same law, okay? We can just remember this rule here, because if A and B are mutually exclusive, then this part is equal to 0. That's why we end up with this formula here. So you can just remember this one if you want to. Let's look at an example. A card is drawn from a standard deck of 52 cards. Find the probability that it is a queen or a 2. So or means plus. So we want to find out the probability that it's a queen plus the probability that it's a 2, take away the probability that it is both a queen and a 2. Can it be a queen and a 2? It can't, can it? That's actually equal to 0. These are mutually exclusive. If you think about the queens, we've got 4 queens. You know, they are the hearts, diamonds, clubs, and spades. And we've got 4 twos. 2 of hearts, 2 of spades, 2 of diamonds, 2 of clubs. There's no overlap. So this part is equal to 0. We can cross it out. Now let's do the probabilities. The probability of a queen is 4 on 52. Probability of a 2 is 4 on 52. Add them up, we get 8 out of 52. Now what about a queen or a red card? Okay, is there overlap here? There is, isn't there? These ones are not mutually exclusive, so let's think about it. It's going to be a probability of a queen plus the probability that it's red. Take away the probability that's queen and red. Alright, probability of a queen is 4 on 52. Probability of red is 26 on 52. How many red queens are there? There are 2. So have a look at that. I could have written this as a half. It's just easier with fractions though to have the same denominator. So 4 queens plus 26 reds take away the overlap. Gives us 28 and 52, which is 7 on 13. Here's another example. So we're returning to Jana tossing the coin and the 6-sided die. What's the probability that she throws a head or a 4? So here's our formula. Now it's going to be the probability of heads plus the probability of a 4. Take away the probability that she throws heads and a 4. Okay, probability of heads is a half. Probability of a 4 is 1/6. But what is the probability that she throws heads and a 4? This is our law of multiplication, isn't it? So it's going to be probability of heads times the probability of a 4. So just have a look at that for a second, make sure that makes sense. It's a half, that's the probability of the heads, a 1/6 minus a half times a 1/6. And when we calculate that, we get 7 on 12. Now, if we list the sample space, we can just count them up. So heads or a 4 means all of these guys plus that one. So it's 7 out of 12. And it's up to you which method you use. Of course, sometimes they will give you a question without context, like this one. So we've got the probability of A, the probability of B. We're asked to find the probability of A or B, and we're also given the probability that A and B occur is 0.15. So quick question, are these events A and B mutually exclusive or not? They're not mutually exclusive. Do you know why? Because this is not equal to 0. So there is an overlap. So we need to use the full formula. There we go. We're just going to substitute in now. So probability of A is 0.5, probability of B is 0.3, probability of A and B is 0.15. And let's put it in the calculator, we get 0.65. Just before we finish, I want to return to this question because it's possible to have both laws together in the same question. 12-sided die is thrown twice. Find the probability that we get a 2 and an 8 in either order. So remember before, we worked out the probability of a 2 and an 8 and then we doubled it. But we could rewrite it like this. It's the probability that we get a 2, then an 8, or we get an 8, then a 2. And in probability, or means plus. So it's the same as this. Probability of 2 is 1 on 12. Probability of 8 is 1 on 12. And so there's our answer. Okay, that brings us to the end of this lesson. It was quite a tricky lesson, so you might need to go over it a couple of times. In our next lesson, we're going to look at Venn diagrams.